Welcome to What Is It About the Weather? I'm your host, Mark Jelinek, and this week we're going to be talking about why don't I get that weather? But before we jump into our main topic, let me just say, as always, I hope you've had an enjoyable, interesting, intertwined, adventurous even maybe, I don't know, mostly positive, of course, intertwined weather week. I know since we last talked, I've kind of been in the weather, kind of in my photography mode this week. For the first time in a while, I had a setup that actually was conducive. You know, I for any of you who follow the YouTube page, go in there and follow. If you don't, subscribe. Or my photo page where I post various photos that I take over time related to the weather. You'll know that you go through dry periods where it's almost tough to find things. And this is a struggle for anybody, right? Because what you or someone else might find interesting, I may go, well, I've seen that before, or I've done that before, or that's not particularly interesting. So I do try to think about things from a different perspective from time to time. But today, I'm able to look back at this week and say it was sort of classic in terms of some of the weather that I had. So for the first time since I got this new DSLR camera last year, I had a good setup for shooting lightning. Now, I had bought a filter that you can put on the end of the lens that theoretically will allow you to shoot lightning in the daytime, and I'm still not figuring that out. But one of the things that is different with a DSLR is all the zooming being optical, unlike a phone. When I capture video, I am actually able to capture some locations with more clarity at a distance. So I was able to take some shots doing them from frames from the video, which was nice. But finally, nighttime came and I was able to get some shots, some nighttime lightning shots in the open with this camera. And the results were amazing. A lot of times when you look at a small version of a picture on the phone or even on your tablet, you can't grasp the detail. I mean, you can kind of understand it or see it, but it's not until you get on a bigger screen that you kind of just go, wow, look at all the minutia that's going on there. And I had this lightning shot that fit into that. So, I posted it on Instagram and Facebook and Twitter, those sort of things. But I think the only people that really grasped what was there and how nice the shot was were people that actually were looking at it on a PC. But I'm by no means a professional photographer, as we know, but this was a moment where I felt really good about, one of the pictures I took. I'll put some more of these. If you don't need to follow the page, but you can. I have a Google Photos album that I put out there called Weather and Me. And, of course, it's dominated by things like sunsets and lightning shots because those are very vivid, but I have some other things as well. And you can even also see the evolution of my photography over the past year. There are things that I posted a year ago, and I leave them there because, there's no reason to take them down. That there's no way I would put the same picture out there now. Right? And that's good. It means I'm evolving and improving. But I'll put this lightning shot, it's one of those times when, and this doesn't happen very often, I had so many good lightning shots to choose from, trying to pick your favorites can be a difficult thing. So they'll be out there. And to get there, all you have to do is go to whatisitabouttheweather.com/photos. And that'll take you to the page instead of trying to get some link from me. Then I'll put it in the show notes anyways, but that's the easy way. whatisitabouttheweather.com/photos. And again, if you are connected to, it's still kind of built out of the old Google Plus stage, but if you've got a Gmail account or something, you can essentially subscribe to the page and be kept updated. And I update it like once or twice a month with some new photos, as long as I've had a chance to go out and do something. But at least once a month, I put some new stuff in there. So I don't burden everybody, right as I take the pictures. It's just kind of a nice summary, and that way you get to wait until see my good ones, unlike maybe Instagram or Twitter, where I'm more likely to push stuff out quicker. So that's where I've been intertwined this week is in the creative photography mode. But let's talk about, because I mentioned one of those things about lightning. Why don't I get that weather? Now, one of the premises of this show has never been to get focused on the weather per se. Not talk about a weather forecast or what your weather's going to be this week or where's that tropical cyclone going. I could do a podcast every day on those topics. But it's not necessarily relevant for you, and I really do like to keep the show interesting, but also educational. And within that context, I still think this could be a useful topic. The idea, now, we had the You Ask, We Answer series, and it covered sometimes some more of the scientific, or what I would call scientific, weathery type topics. But I haven't really done it here because they are better suited for that generally. They're better suited, in my mind, for a 5 to 10 minute video, or even if it was just audio, but the video helps explain it. Here, though, I had a suggestion from a listener a long time ago. Aaron sent this in, and actually he had sent in the things about, which radar apps and precipitation apps do you think are best. But I've been kind of sitting on his because he's up in the Pacific Northwest of the U.S., and for those that don't know, this is an area that does not get much in the way of thunderstorms. And I think he knew scientifically, this is one of those cases where I think he knew darn well why he doesn't get that weather, but he thought it would make a good episode, and I tend to agree. So I've picked 4 items to go over today. In the future, we may cover other ones. There's some additional ones that I thought could have been covered, but it's not like, this might be something like weather in history, or, did weather change history? Maybe it's something we can come back to from time to time, but I don't think it's going to be a regular thing. I looked at, should it be an end of episodes sort of, segment? And I thought about that, but I'm not sure it really fits there. So we're going to do this, and we'll see how it goes. We'll see if you like it, and hopefully you'll become more informed than you had been before, because you're going to be looking at it with 2 different sets of eyes. Either you've experienced these things and are familiar with it, or you haven't. But in either case, you may have not thought, especially if you lived in one place all your life and you've always had this weather, really other people don't get this, and why might they not get it? And for those that don't know, you got a reason to go check it out, look for it. So let's dive into it. Like I said, this came from Aaron, and specifically he was asking about thunder and lightning, or essentially thunderstorms, on the west coast of the U.S. So let's start there. Let's start with lightning, all right, specifically. Now, thunder is a byproduct of lightning. We all know that. Although you can have lightning without the corresponding thunder, right? We had some of that this week here. We call it in the South and have traditionally called it heat lightning. It's not really produced by heat or anything. Some people now call it silent lightning. And all these are just descriptive words to try to explain lightning you can see, but it's happening so far away that you're not getting the audio component of it. That's all. That's all. It's still happening. It's just the sound waves don't reach you. But what's key, and why not on the west coast of the U.S., as an example? So with all these segments, I'll have some places you can go and look about lightning or the other topics, about why certain things occur in different regions or where they occur, so visually you can make that connection as well. But very simply, to get lightning, we need vertical motion. And we need vertical motion because what you need is you need to have this separation of particles that happens in clouds. Okay, so we need vertical motion and condensation, really. So just plain up vertical motion without moist air isn't going to get us there. But what contributes to thunderstorms and gives us lightning is this vertical motion allows for the separation of significant distance of positive and negative charged particles. So as you can imagine, even if you have clouds, if they're all kind of together at one level, you don't get that separation. So you need this distance. So moisture, vertical motion. Vertical motion is most often caused by instability. And what leads to instability usually is this difference in temperatures when we get into areas like the mid-latitudes. Now, we're going to talk about a case shortly where sometimes it's just the ability to have a heat source available. And that's why in tropical rainforest or, the tropical areas of the planet, it may not go down the same way, but the idea is still the same. You need this vertical motion. So the instability just happens to work a little differently. I'm not going to delve into that too much today. But in any case, that vertical motion and condensation allows these particles to get separated, and ultimately they've got to equalize. And that's what lightning gives us. Now, in the case of the western U.S., it's up against a cold part of the Pacific Ocean. So the West Coast U.S. mostly has really cold water. This tends to stabilize things. And this is not to say that the West Coast of the U.S. doesn't ever get thunderstorms. They do on occasion. But just in comparison to the eastern half of the U.S. or areas where we get more of this instability, a lot of temperature variance over the continental U.S., or as I mentioned, in the tropics and tropical rainforest, where you can get these huge, what seem very stationary, and a lot of times they are, thunderstorm events, that vertical motion is key. So vertical motion, moist air, thunder and lightning, there you go. So if you're not in an area that has a lot of this, and you may have never thought about it that way, right? You may have not realized that, oh, I have a fairly stable atmosphere above me where I am. So that's lightning. Again, the show notes will have a little explanation. I put at least 2 for each one of these scenarios because there were some really good write-ups from people I mentioned before, like Dennis Mercereau, who had done a piece on this a couple years ago. He did a really nice write-up on just thunderstorms in general, and specifically about the West Coast of the U.S., but this can happen anywhere. I mean, if you go to the polar regions, they're not as inclined to have these sort of things. Cold ocean waters, and Chile was the same place. I lived there for many years. The thunder and lightning, if it did occur, usually was over the mountains because that's where you started to get this heating and this instability that took place. Sometimes, every so often, that would work its way down into Santiago proper. But generally speaking, it wasn't because it was regulated by the cold current off the Chilean coast, as was much of Chile. Fog, which we're not going to get to today, plenty of it. But thunder and lightning, not so much. All right, let's move from a little thing, like an individual thunderstorm, to something big and tropical with lots of lightning as well, which is tropical cyclones. Now, tropical cyclones, you do have to think a little differently. Fundamentally, at their core, they behave differently than the thunderstorms I just described over, for instance, the continental U.S. or continental Europe, or any area where you have these big temperature differences. And again, I don't want to delve deep into the science, but there's words that you use with a thunderstorm. One's called baroclinic, and ones that you use with tropical cyclones or thunderstorms in the tropics called barotropic. But they're 2 different formation types, right? And it has to do with what the temperature profile is as we go up in the atmosphere. With tropical cyclones, we're actually looking for something different. We're looking to take advantage, and this is what happens for nice, warm, and hopefully deep warmth in the ocean under which it's forming. So it needs that, and then it also needs this other little kicker, right? Some sort of low pressure area that can start as a baseline from which to grow. And that's always the challenging thing with a lot of these things with weather. It's like, why does it finally reach that threshold? Well, in the past, I've had the pleasure, and I've mentioned James Belanger on the podcast before. He did work with his thesis work related to what we call African easterly waves. And anybody who follows hurricanes or tropical cyclones in the Atlantic will have heard this term. And maybe you have in other basins as well. But generally speaking, you've got this pulse of energy, this area of low pressure, and a lot of times it might move off a continental area where it's benefited from a different type of instability, moves over warm waters, leverages those warm waters, and becomes a tropical cyclone. Yes, that's simplifying things tremendously, but that doesn't matter. So we've got this nice warm heat engine with it. And when you go back to the energy episode I did back in May, I believe it was, or late April, we talked about tropical cyclones and the tremendous amount of energy they have. And it's really fueled by this warmth in the ocean waters. Again, we're looking for vertical motion, but as I mentioned, it's something we call barotropic vertical motion. And barotropic is just a state of the atmosphere where temperatures tend to be the same temperature all around. Okay, so to the north and the south of a tropical cyclone, the air temperature might be similar, whereas baroclinic is just referring to these areas where we tend to have competing air masses, warm versus cold, that give us different types of outcomes. But if you have that warm water and you're able to fuel it, you have this low pressure center that kicks in, and again, a few other mixes and pieces just to keep it simple. That's what leads to tropical cyclones. But if you look at the map, if you go and look at one of the maps in the show notes, you'll see the key is, where are these warm waters? And also, where are they in such that you have these more uniform temperatures? Right? Because we get, as an example, we have a thing off the eastern coast of the U.S. called the Gulf Stream. It's actually very warm waters. And tropical cyclones tend to thrive there. And it's one of the reasons that a tropical cyclone can essentially make it all the way to Europe, because this warm water goes all the way from the U.S. over to Europe. And they can form there, but they don't generally. They form and they have kind of a different formation approach. But even for them to form there, a low pressure system might, for instance, move off the U.S., but it has to transition to go from this type that are used to producing thunderstorms in these competing air masses, as cold and warm, to be called what we call a warm core system. It just has to become a different animal and evolve into something different, a different sort of beast. And that's why you tend not to have as many, because the systems tend to be a little faster moving up there. So right circumstances, it can happen. But this is why they tend to happen in more of what we call the tropics, but not just any part of the tropics. It's got to have the right water. And this is why we tend also not to see them form in the southern Atlantic, because the cold waters there don't contribute to the formation. So it's these combination of things. But if you're wondering why, for instance, I live in Brazil, yet don't see tropical cyclones, or why, for instance, and we talked about this a little bit with the West Coast U.S., the East Pacific Basin, which is, just over from the Gulf of Mexico on the other side, the West Coast of Mexico, lots of tropical cyclones form there and across the west coast of Central America. And quite often, some of them are fueled by these waves I mentioned coming all the way from Africa. But the life of the storm tends to be regulated by these warm waters, or lack thereof, as you move further north quickly. So while the U.S. has the Gulf Stream, the West Coast U.S. doesn't have this nice warm current. It has a cold current. So the other thing you'll kind of catch, and it'll become obvious, is the flow. The flow of these systems tends to be from east to west, which is a behavior and a pattern we see in the tropics, because the spin of the Earth isn't impacting things as much yet, like it does when you get into the mid-latitudes and the polar regions, which tend to kick things back from west to east. So, are you in the tropics? If you are in the tropics and wonder why you don't get them, think about maybe the cold weather. But take a look at the maps and see. If you're not in the tropics, now you understand you got to have this warm water. So, there you go. There's number 2. Now, tornadoes. And I get this, again, most of these I hear questions from people, and I tend to answer them when we have the conversation, because I just get it to talk about weather as we go along. But this is another one that's good because it's even more constrained. A lot of people get, let's say, thunderstorms, as I mentioned, and lightning. Not everywhere. But that doesn't mean that tornadoes come along with it, because tornadoes need something a little different. They, unlike a hurricane, feed on this variance in temperature. They actually like it to be cold and hot. Now, one of the basic fundamental tenets of our planet is, and physics is, I shouldn't say our planet is, warm air wants to rise, where it becomes cool and it reaches a point of buoyancy and it settles in, right, or whatever. But if you have a situation where you got some cold air aloft, which is normal, and you got some warm air at the surface, which is normal, but we've kind of talked a little bit about this in the past, like at nighttime when things first happen, and this could be, like I said, a future episode for fog and why we get fog, or smog even. It has to do with the way the earth cools and the surface cools. But every so often with tornadoes, we get a slightly different scenario, where most locations that we look at tend to have what we call this temperature inversion. And this keeps all the air from the surface as it's heating from just running wild every day. Now, in some places you're at, it does kind of run wild every day. If you're in a place that gets thunderstorms, tropical rainforest is an example again. But generally with tornadoes, we get this capping. And so we've got this cold air aloft. It's ready to be all mixed up. We've got this hot air at the, or warm air at the surface. It's all mixed up. But we have an even warmer layer kind of in between that caps it. Particularly, it might be dry as well. And it keeps that warm air down below from going too much higher. So basically, you think about temperatures as we go up in the atmosphere, you would logically think, and this happens in our area of the planet vertically, that temperatures decrease with height. But we get this sort of capping situation that keeps this area, so the surface gets warm, the heat of the days warm it up, and the air's getting warmer and warmer and warmer. And eventually it crosses that threshold where it can just run wild, and it goes way up. And this is where we see these large cumulus clouds form. And you've probably seen them if you're in an area that gets good thunderstorms, as an example. You can see these things, these towering things go up. But it really is this contrast of cold and warm air that creates this vertical mixing, right? And this behavior of up and down, not just one direction, not just up, but up and down motion that gives us the type of thunderstorms that we get that give us tornadoes. And this is why tornadoes only tend to happen in some regions. Now, the U.S. is sort of home to tornadoes. Roughly, I think it's somewhere to 70 to 75% of the annual tornado mix happens in the U.S. And it tends to happen in an area, probably one of the biggest, they call it Tornado Alley, and it's an area kind of straddling where warm Gulf moisture can flow north into the U.S., and the dry air coming out of the Rocky Mountains. And that's what I'm saying. So it's not just about getting hot, but it's about these contrasting air types that really make the difference quite often. But even where I am, it's called Dixie Alley for the southern states here in the U.S. It's a zone that also gets a lot of tornadoes. But if you look at the maps, and again, you can see this, there's just, if you were to look at thunderstorms, a big area, tropical cyclones, even by surface area of the earth, big area. Tornadoes really narrow down. And they can stretch into Canada for certain times of the year. Like I said, the U.S. and the map that I've put up there has kind of these bullet zones. And so you really get an appreciation of where these things can occur. A little area down in Uruguay and Argentina. And actually there's been some really strong tornadoes there recently. And I've seen some incredible videos in the past couple of years. You've got some zones like certain parts of Australia, certain parts of Southeast Asia, certain parts of that buffer zone between the Himalayas and coming off of it in India, certain parts of South Africa, a good chunk of Europe. But if you look overall compared to the planet, it's not necessarily a lot of the planet. And some of the areas, given the type of terrain that you need, are also not the most densely populated, which doesn't mean that tornadoes can't occur in the cities, right? It just means that a lot of the conducive zones happen to be in areas that aren't as heavily populated as other areas. So again, it's not just, as we've talked about with thunderstorms can form under different types of conditions, but it is the kind of the thunderstorms that miss the western U.S. that are the primary driver of tornadoes, which is why we tend to see it. But it's that mixing of nice dry air, but really hot dry air, and moist, warming up air, and then that cold air aloft. Like I said, it's all those things that really mix in that give us tornadoes. So the last one, and I had to go cold season weather on you. You knew I had to do this. Now, there's lots of parts of the globe that never see snow, at least at the surface. Higher elevations, you can almost always get to it eventually. But there's, again, you go into the tropics of the world, unless you're in a really high mountain, you don't see it. Now, as an example, you can go to Hawaii And their tall mountains do get snow. They even got a ski resort on the top of it. But the lowland people aren't thinking about snow on a regular basis. But I wanted to talk about a specific type of winter precipitation. Now, most people think about snow, and that is the most common. Far and away the most common. And the second is freezing rain. And essentially what's going on with freezing rain is you've got some warm air in the mix somewhere in the atmosphere that just happens to melt the snow. But for whatever reason, for instance, radiative cooling or something else, or a cold front starting to push through near the surface, but it hasn't pushed through all the way yet into all layers of the atmosphere, you get this freezing rain. And I talked about a freezing rain event being how my fascination with the weather started, right? The setup happened to stay in place for a very long time. We're very near the surface. It was cold. It had gotten cold. But aloft, it was nice, kind of warm, wet air. And that contributed, that borderline being so close to freezing, actually, the air can hold, we're not talking in a relative sense, but in a pure sense, it can hold more moisture. And that's what led to the severity of that event. And freezing rain is what you see when it sticks to trees and power lines and any elevated surface, and you get that kind of teardrop effect. So you might see these long icicles that form. And actually, that's kind of what goes on with icicles in an effect is, let's say during the day, sun comes out, it's melting snow on a roof, all that water's dripping down, and then eventually, as the night cools off, it gets back below freezing and it forms those long icicles. It's essentially the same idea as freezing rain, except freezing rain is happening as the precipitation is falling. But there's an element in there called sleet, right? And sleet is a very interesting kind of in-between state. So mostly snow, even less freezing rain, and even a lot less sleet. Now, sleet happens when you have what we would call a warm nose in the atmosphere. So at the surface, it's cold, right? And aloft, it's cold. But there's this very tiny section. It's got to be high enough up where you have a nose. And I hate to quit bringing James back into this. I guess I should have told him I was going to do this to him, but we had this event this past year in Atlanta where we got sleet, and he correctly identified there was this big debate about whether Atlanta was going to get a lot or a little bit of snow, and we didn't get much where I was. We got mostly sleet and freezing rain. And he very properly noticed up in the profile of the atmosphere that there was this warm nose, and he's like, this has got to break down or otherwise we're not going to see snow. And it didn't for us. So that little nose, any snow that was coming down, and you know, it's kind of interesting when you think about rain. Rain falls fastly as things fall out of the sky. But snow is actually much slower, and I've seen estimates of anywhere from 45 minutes to an hour, depending on how high in the atmosphere it starts, that a snowflake can take to reach the ground. And so it's actually falling relatively slow, so it's got time to melt, right? So it goes through this little warm pocket, and it's moving kind of so slow that it melts a little bit. But then there's that cold air underneath that's pushing into the region or entrenched in a region that refreezes that little piece of water before it reaches the ground. So this is the difference between that and freezing rain. There's enough cold air in the vertical profile of the atmosphere for that water to refreeze. And that's what gives us sleet. And I did a little video on it back in the YouTube, so another reason to go to the YouTube channel. Because sleet's this really neat thing. Okay, some people want to talk about difference between sleet and hail. We may do hail another time, but it really is they're two different sort of animals we're talking about here. Sleet is usually not very destructive in its falling. Hail can get big, as you know, and break through roofs and certainly dent cars. I've had to deal with that before. But sleet falls, and it just makes this neat sound because it's bouncy, and it does. It literally bounces around, and it will eventually kind of usually melt together and form a layer, just like freezing rain will. But it doesn't work the same way. So you kind of need cold, warm, cold. Now, those are 4 types. The only one I've never personally dealt with, I've never seen a tornado firsthand. I'm not sure that I'm in any hurry to. I do think it'd be neat. So there's a lot of that I've had the experience of. But hopefully today, for those that don't experience it, or even if you do, you've got a different perspective of why you get it, Or why, darn it, why don't I get that weather? All right, time to let you go. Time to move on. You know, there is an interesting connection between. James gets a 3 for today in the episode. James did some research on tornadoes and tropical cyclones or hurricanes and about predicting them. Did you know that the differences, again, as those hurricanes make landfall and they're transitioning to a different type of weather zone, they can actually spawn, all this energy can help spawn tornadoes. And it can be as many as 100 or more in certain circumstances. And there are certain cases where they spawn more or less. But James had developed a model to kind of look at predicting how many tornadoes might come given the type of setup that you're experiencing with that hurricane or that tropical cyclone as it's making landfall. So there is a connection even, though they tend to form in very different ways. All right. I had something, somebody had asked, you know, I got some other questions that I didn't get to last week, and I'm going to put this off because I see that I'm already over 30 minutes. But someone asked about the actual setup that I use to record, and I promise to get to that in the next episode. I'll make sure that there's time. But let's wrap up here and just say thank you for your support. You know the RSVP method. Rate, share, validate, and pledge. Just go to whatisitabouttheweather.com/support to learn more. And thank you for those that do support in the many ways that you do. If you want to reach us, you can also go to whatisitabouttheweather.com/contact, or you can also just pop me an email at whatisitabouttheweather@gmail.com. Again, this show is particularly conducive to show notes, so you'll find more, some on each one of these 4 topics, so you can learn more and make a further jump deeper into the science if you want to. If you feel that you've read these things and you still want to know more, just ask me. I'll have that conversation with anybody. But until next time, may you have an interesting, enjoyable, intertwined weather week. May you experience some of these things if you haven't, or at least know more about why you do get them or why you don't. But no matter what, may you find some way this week that weather is intertwined in your life and hopefully impacts it in a positive way. Because as we all know, there's much more to weather than the weather itself.